We saw the other day how to draw the basic inverse trig functions. Let's now have a look at some variations to it. Instead of just the basic inverse sine of x, we had 5 inverse sine x on 3. How's our domain and range affected? How do we work it out? Well, we know the regular inverse sine curve goes in between -1 and 1. So the only difference here is instead of x, we've got x on 3. So we can say, well, the domain is now x on 3 goes in between -1 and 1. Multiply everything by 3, we get our domain. It's in between -3 and 3. Now the range, remember when we're talking about range, we want to group the number with the y. So that 5, it'll become y on 5 is in between -pi on 2 and pi on 2. And that gets us -5 pi on 2 to 5 pi on 2 as the range. So now we can draw it. Now, I suppose theoretically, if it's the only graph you're drawing on the axis, you could draw exactly the same graph, just change the numbers on it. There it is. So there's our y equals 5 inverse sine x on 3. Ooh, this one's a little bit more interesting. Inverse tan of the square root of 3 minus x squared. Now, normally the domain for inverse tan is all real x. However, we're substituting into the square root of 3 minus x squared. So that no longer means we can substitute any x value in. So for this one, we've got a problem with that square root sign. We're going to have to take that into account. So 3 minus x squared, well, we know that's got to be greater than or equal to 0. So therefore, the values we're substituting in will go in between minus root 3 and root 3. That now means we've got restrictions on the domain. How's that going to affect our range? Well, now, when we're substituting the x, we're going to stop at root 3 and minus root 3. So let's see what happens there. Well, actually, at root 3, we'd end up with 0, because we've got inverse tan of 0, which is 0. And the same at minus root 3. Okay. Well, that's not telling me a lot about the range, other than it stops at 0. So when we have these symmetric, because inverse tan is a nice symmetric graph, restrictions on domain, endpoints, the other good one to have a look at to try and work out the domain is the midpoint. So let's see what's happening in the middle. X equals 0, we got y equals inverse tan root 3. Root 3, the exact value is 60 degrees, which is pi on 3. Okay, so our range is going between 0 and pi on 3. So what on earth does this look like? It's certainly not going to look like an inverse tan curve, because now we're starting down at 0, going up to pi on 3, and then down to root 3 is going to be 0 as well. We know it's symmetric, something like that, I guess. Something like that. All right, now this interesting one. The inverse sine of sine x. Normally, there would be a restriction in the domain, because we know inverse sine goes in between -1 and 1. So for this one, sine x will go in between -1 and 1. But sine x always goes in between -1 and 1. So actually the domain for this one turns out to be all real x, because it doesn't matter what we substitute into sine x, we're going to get a number that's in between -1 and 1. Now what's going to happen with the range then? Well, the range is not going to change, because if I can get every value from -1 to 1, then I must be able to get the complete range as well. I guess another way of thinking about this is, logically when you look at it, inverse sine of sine x, you're expecting it's going to look something like y equals x. It's going to have something to do with that. So let's just draw it over here. So it's y equals x, but the range is minus pi on 2 to pi on 2. Well, there's y equals x, going from minus pi on 2 to pi on 2. But we said the domain was all real x, so what's happening? It's either going to be a series of parallel lines of y equals x, or we might get a zigzag. How do we tell? Well, I guess we could just test some points. If we sub pi into that, no, pi is probably a bad one to pick, isn't it? Because we'll get 0, and that won't tell. If I sub pi in, I'll get 0, yeah? But that's not going to tell me whether it's parallel or whether it's a zigzag. It's going to be, so maybe 3 pi on 2, 3 pi on 4. Wouldn't 3 pi on 2 be easier? So sine of 3 pi on 2 is -1. inverse sine of -1 is minus pi on 2. So over here at 3 pi on 2, we'll be down at -1. So it looks like we're going to have the zigzag. So inverse sine of sine x is a nice zigzag. Let's do it the other way around. Sine of the inverse sine of x. So this time we're substituting in, but we're substituting into inverse sine x. So our domain is going to stay at -1 to 1. Because that's the only thing we can substitute in to inverse sine of x. The range, well, let's have a look. It's a restricted domain now. So when x equals 1, we get the sine of the inverse sine of 1, which does cancel and give 1. When x is -1, sine of the inverse sine of -1, and again that turns out to be -1. And what the heck, let's have a look at 0. Sine inverse sine of 0 does give 0. So it looks like our range here is -1 to 1. It kind of makes sense because we're expecting it to be based on y equals x. And if the domain's -1 to 1, it kind of makes sense that the range would be that as well. So this time, instead of a zigzag, we just get that piece of the line, y equals x. So 17c, we're going to play with looking at the inverse trig variations.